Mechanical energy balance is very useful in furnaces in several ways. A large amount of products of combustion, they flow from the furnace to the flue and ultimately to the stack to be discharged into the surrounding. It is required to design a blower or a fan to increase the rate of exhaust of products of combustion. Also, a large amount of fluid, for example air, is also used. Metering of this air, one requires various flow measuring devices. So, in fact, efficient utilization of fluid is very, very important for the thermal efficiency of the furnaces. So, it is in this respect the mechanical energy balance is very useful, and this mechanical energy balance takes into account the properties of the fluid at the inlet and at the exit only. We have derived the mechanical energy balance in the form of various properties, and today we will see the applications of the mechanical energy balance in order, for example, to design the fans or the blowers and so on. In fact, mechanical energy balance is also called Bernoulli equation. In the mechanical energy balance, which is also called Bernoulli equation, care must be taken that it is based on per kg or per unit mass of the fluid. So, in order to get the appropriate result, one has to multiply by the mass of the fluid that is flowing. So, let me illustrate the application of the balance by solving few problems. So, first of all, let us take, say it is proposed to install a fan to draw air at rest, in a horizontal rectangular duct, of 250 millimeter into 350 millimeter cross section, whose length, that is length of the duct, is 60 meter. The air enters the duct at 298 Kelvin and 755 millimeter mercury at 30 meter cube per minute. Now, you are required to calculate. So, let us calculate the horsepower of the fan. Calculate the horsepower of the fan if the fan discharges air at 755 millimeter mercury pressure. So, for this condition we have to find out what should be the capacity of the fan in order to meet the objective which is there to draw air at 30 meter cube per minute. So, let us see now. Now, if I represent in a form of a diagram, then it looks like this. Say this is a duct of rectangular cross section which is say here somewhere air is entering and somewhere here air is discharging. So, this is the expansion, this is the expansion, and here when the air enters into the duct it contracts, when air exits the duct it expands. So, this is given to us, it is 60 meter. So, here I have to install a fan. So, air will enter and somewhere here air will exit. This air will exit. So, in this, as the air enters, so air contracts as it enters in the duct. Here as air exits, the air expands as it exits. So, as such also given to us, so EF1, if you recall, this is the friction loss due to contraction, friction loss due to contraction is given to be equal to 0.4. Similarly, EF2, which is the friction loss due to expansion, friction loss due to expansion, that is given to us 1.0. Also, it is given to us say viscosity of air, which I represent mu of air, which is the viscosity of air, is given to us 1.78 into 10 to the power minus 5 kilogram meter second square. Also, in solving these particular problems, many a times the conversion factors are also important. So, well, it is given here, say 1 millimeter mercury, that is equal to 133.2 Newton per meter square. So, now we have to find out what should be the capacity of the fan. So, the first thing that one has to do to apply mechanical energy balance is to locate the position 1, that is the inlet, and position 2, that is the outlet. So, as such I am locating, this is the position 1, inlet, and somewhere here I am locating my position 2. Now, I will write the mechanical energy balance as we have derived. So, mechanical energy balance is G Z2 minus Z1 plus V2 bar square minus V1 bar square upon 2 plus P2 minus P1 upon rho plus F minus M is equal to 0. Now, if you recall, Z2 and Z1, they are the height to which the system is raised from the datum, and as such it will introduce potential energy into the system. V2 and V1, they are the velocities at the exit and at entry, that is precisely at location 2 and location 1, and P2 and P1 are the pressures, F is the frictional forces, and M is the mechanical energy, that is whichever way, whether the system does or surrounding does. So, now if we apply this particular equation to the problem, we see that Z2 is equal to Z1, Z2 is equal to Z1, also P2 is equal to P1, because the air discharges at the same pressure at which it entered. So, there is no pressure gradient, and since the velocity at 1 and 2, they are very, very small. So, what we will say that V2 that is equal to V1. So, our mechanical energy balance, if we apply this thing to this, then mechanical energy balance simply becomes F minus M, that is equal to 0, and we know that F is the frictional forces, and so I can write down F that is equal to frictional forces, that is 2F L upon D V bar square plus half EF2 V bar square. So, that is the frictional forces. So, all that we have to evaluate friction factor, and we have to calculate V bar. Now, remember, the V bar is different than V1 and V2. V bar is the velocity of air inside the duct, because this particular velocity will decide the loss of pressure due to frictional forces, because for the frictional forces to be operative, the air should cling to the wall of the pipe. So, I will again stress that V1 and V2, they are different than V bar. V1 and V2, they are the velocities at entry and exit, where V bar is the velocity of air in the duct. So, now we have to evaluate this thing. Now, since we are having a rectangular duct, so we can replace D by an equivalent diameter. So, in terms of, that means for rectangular duct, we can write down M, that is equal to 2F L upon DE, where D is the equivalent diameter, V bar square plus half EF1 V bar square plus half EF2 V bar square. So, now we have to calculate the various terms over here. So, first of all, we will evaluate DE. Now, DE is the equivalent diameter, and you recall that is equal to 2 into Z1 into Z2 upon Z plus Z1 plus Z2, and that is equal to 2 into 0.25 into 0.35 upon 0.25 plus 0.35. So, this is how you will be evaluating D, and that is equal to 0.292 meter. Now, we have to evaluate the density of the air. So, we can calculate rho, that is equal to P upon RT, and P is given to us, that is 755 millimeter of mercury into 133.2, that is become Newton per meter square, that is the gas constant 8314 divided by 29, and temperature is 298. 29 is the molecular weight of air, and it comes to 1.18 kilogram per meter cube, that is the density. So, now we have to evaluate V bar. So, V bar, we are given 30 meter cube per minute, that is 30 by 60 into cross section area, that is 1 upon 0.25 into 0.35. So, that is equal to 5.71 meter per second. So, now we have evaluated, and also we have to evaluate the value of the friction factor, and for evaluation of friction factor you have to calculate the Reynolds number, and as you recall I given the expression that friction factor that is equal to 0.0791 Reynolds to the power minus 0.25. So, you calculate the Reynolds number, that is V bar rho upon mu, and for that I have given you the value of mu. So, one can calculate the Reynolds number. So, the Reynolds number would be from here. Reynolds number that will be equal to 0.292 into V bar, that is 5.71 into 1.18, that is the density of air, divided by 1.78 into 10 to the power minus 5. So, the Reynolds number will be equal to 1.105 into 10 to the power 5, and from here I will be getting F, that is equal to 0.0043. Now, in the equation m is equal to 2f L by dE V bar square and so on, all terms are known to us. F we know, dE we know, V bar we know, EF1 and EF2 are given to us. All that we have to substitute and get the value of m. So, now I substitute. So, m that will be equal to 5.71 into 5.71 2 into 0.0043, 60 is the length of the pipe, divide by 0.292 plus half into EF1 plus half into 1. So, that is what we will get it, and if you solve, then I will be getting here 80.94 meter square per square. That will be the work done by the fan. That will be the work done by the fan. Now, the value is plus, that means an additional mechanical energy will be required by the fan. So, we can calculate now the power, that is we have to calculate the power of the fan, because when you go to the market to buy the fan, you have to tell him what horsepower or what kilowatt capacity of the pump is needed in order to meet your objective. So, in order to calculate the power, all that you have to multiply the mass flow rate of the gas. So, that becomes 80.94 into 0.5 into 1.18. So, that has become the power, and if you want to be still sure, then you can do the dimensional analysis, that it will be meter square upon second square into meter cube upon second into kilogram upon meter cube. So, from here the dimension which emerges, this gets cancelled. So, emerging dimension is kilogram meter square upon second cube, and all of you know this is the dimension of watt. So, that is how we get the wattage, and from here we will get 0.048 kilowatt. Now, in order to calculate the horsepower, say 1 kilowatt, that is equal to 1.341 horsepower. Therefore, the horsepower of the fan, required, that will be equal to 1.341 into 0.048, and that will come out to be equal to 0.064 horsepower. So, that is how you can apply the mechanical energy balance equation to calculate the capacity of the fan. In many cases it is required, say for example, for disposal of the products of combustion you require to create an extra pressure. So, that is the way you will be calculating. Now, just as an exercise, what you can do is that you apply the mechanical energy balance for the following situation. So, I am drawing in a sketch same problem. So, this is the duct, and what I do now, the plane 1 I retain as it was previously. This is the plane 1. Now, what I am doing now, I am shifting plane 2 at the exit of the pipe. This is my plane 2, this is my plane 1, and this is again the same rectangular duct. All dimensions are same as what we have done just now. What you have to apply now, the mechanical energy balance as shown in this particular diagram. The plane 2 I have shifted at the exit of the duct, which was in earlier problem beyond the exit of the duct. So, all that you have to apply the mechanical energy balance for this particular system, use all the values whatever you require, which has been just now given to solve this particular problem, and calculate the work done by the pump just by shifting plane 2 at the exit of the duct. So, if you do that, then the M value according to me coming to 80.43 meter square per second. So, this is a exercise to be done as I have illustrated what is to be done. Now, in another situation, say there is a melting area, and the air above the melting area is often contaminated with the particulate matter. So, from the environmental point of view, it is not good, because then the air containing the particulate will be inhaled, and as such it may affect the health of the people who are working around the melting environment. So, let us now find out an arrangement where we can clean the air, and for that we have to install a fan or a blower. So, the situation is follows. Now, consider the following arrangement. Consider the following arrangement to filter the air, before it is discharged into the environment. Before it is discharged into environment. And the arrangement is as follows. So, we have a melting area say this is the melting area, this is melting area, and here we have a arrangement for exhaust of the or the cleaning of the air. This is the pipe, and somewhere here we have the cleaning arrangement. This is where here we are required to install a fan so that we can suck the air, and somewhere here we have so this is the bag house. This is the fan. The bag house will retain the particulate, and as such clean air will be discharged into the environment. So, this is the fan, or you can call blower or whatever you want to call. Now, this is 70 meter. This is 52 meter. The pipeline has one elbow. This is an elbow. This pipeline has an elbow that is the vertical pipe and horizontal pipe is connected by an elbow. So, now further it is given that the melting area and environment are at 298 Kelvin and 1.013 into 10 to the power 5 Newton per meter square pressure. Now, it is also given that when delta P, that is the pressure difference across the bag house, is 40 millimeter of mercury, the air flow rate is 58.2 meter cube per minute. It is also given that the elbow, as shown in the diagram, you can consider for the evaluation of the frictional forces. The elbow has an equivalent length, that is LE upon DE, that is equal to 26. You can also consider EF for contraction, that is equal to 0.4, and here EF for expansion, that is equal to 0.81. So, that is what given. Pipe diameter is also given. This is phi, that is the pipe diameter, that is equal to 300 millimeter. So, what will happen? Air will flow. This is the flow of air. This fan or blower will suck the air, and ultimately the air will pass through the baghouse, and here we get clean air. Don't you think this problem is relevant for the environmental cleanliness? So, what we require to find out what should be the capacity of the fan is required. That is, first of all, you will find out the work done by the blower, that how much amount of work will be done by the blower, and from the work done we can find out the capacity of the fan or horsepower of the fan. So, again we have to find out what is our inlet, what is the plane at inlet, and where is the plane at outlet. So, as such, for the application of the mechanical energy balance, the input and output planes are important to show, because it is there you can make the mechanical energy balance. So, I will just draw the diagram to illustrate the plane 1 and plane 2. This is the fan and this is our baghouse. What I will do now, I am considering this is my plane 1 and somewhere here is my plane 2. So, I am applying now my mechanical energy balance between plane 1 and plane 2. So, obviously, I can write down my mechanical energy balance G into delta Z plus V2 bar square minus V1 bar square upon 2 plus P2 minus P1 upon rho minus M plus F, that is equal to 0. Now, mind you, here Z1 is not equal to Z2. So, accordingly, we have to take care, but say V1 and V2, they are negligibly small and their square will be negligibly small. Therefore, we can neglect when V2 can be neglected because of a consideration of location of plane 1 and plane 2 can be neglected. So, then our equation will become G into delta Z plus delta P upon rho plus F minus M, that is equal to 0. So, now all that we have to apply this equation, substitute the values and get the answer. So, here again some calculation will be required, because one should be very careful while substituting the dimensions of the various variable in the equation. That is very important exercise in order to substitute the correct dimension, because the result on M you will be getting in terms of meter square upon second square. Hence, all the dimensions are to be correctly substituted. So, first of all we will calculate, say let me calculate on the next figure. Let us calculate delta P. So, delta P is given 40 millimeter, we convert into Newton per meter square, 133.2, that is equal to 5328 Newton per meter square. Similarly, we will calculate density of air, and the density of air from the values from the formula we get 1.186 kilogram per meter cube. We can also calculate P upon RT. Then we have to calculate V bar, that is equal to 58.2 upon 60, that is meter cube per second, into 4 upon pi into 0.3 into 0.3. So, that is equal to 13.73 meter per second, that is BV bar. Then we can calculate Reynolds number, and Reynolds number will be dV bar upon rho into mu. So, this value will be equal to 2.74 into 10 to the power 5. Now, I can substitute these values, and I know that F, that is equal to 0.0791 Reynolds number to the power minus 0.25. So, I substitute the values, and these values are say 9.81 into 70, because delta Z is 70, plus 5328 upon 1.186 plus 13.73 square into 2 into 0.0791 into 2.74 into 10 to the power 5 raised to the power minus 0.25 plus half into 0.4 plus half into 0.81. So, that is how you will be substituting, and this value will be equal to m. So, m we can calculate from here. So, that will be coming equal to 5856 meter square upon second square, and from here you can calculate the horsepower of the blower. That will come out to be equal to 8.92 horsepower. So, that is how one can calculate this thing. Now, I am giving you some problem for self calculation. For example, it is proposed to install fan to draw exhaust gases at 800 degrees Celsius from the hood of a furnace, from the hood of a furnace. The exhaust gas flow rate, the exhaust gas flow rate is 40 meter cube per minute given at 298 Kelvin and 1 atmospheric pressure. The gases flow through a rectangular duct of 0.2 meter into 0.3 meter cross section. The length of duct before the elbow is 50 meter, and after the elbow (40 meter), as shown in the figure. Say, for example, this is the what the rectangular duct. This is where here the hood, and This is the fan. So, from here to here, this is given as 50 meter. From here to here, this is given as 40 meter, and this is an elbow. This is an elbow of which LE by D E that is given to be equal to 20. This is the fan and this is the exhaust. This is the exhaust, and here given also some values are given, say given EF1 for contraction is 0.4, EF2 for expansion that is equal to 1.0, and the mu by rho kinematic viscosity at 1073 Kelvin that is equal to 1.77 into 10 to the power minus 6 meter square upon second square, meter square upon second. So, you have to calculate. So, you calculate the work done by the fan and power. So, the work done by fan is 8158 meter square upon second square, and power that is equal to 8.8 horsepower. Now, this is what I wanted to illustrate, some of the applications of the mechanical energy balance for the design of the fan, blower and so on. Now, let us look another aspect of the application of mechanical energy balance is in the flow measurement. Flow measurements. Because often we require to know what is the velocity of the fluid, what is the flow rate, we can measure it also and we can calculate also. So, many times we require to measure the pressure differential, and hence we want to calculate the flow rate for design of the instruments for measuring the flow. So, as such the flow measurement they consist of, there are two types. One, they are the velocity meters, and another they are the head meters. The velocity measures, in fact, they measure the pressure, and the pressure can be converted into velocity. And the commonly used velocity meter is called pitot static tube. Head meters, they measure the pressure differential across the flow, and the head meters, they are in fact orifice, venturi meter or venturi, and nozzles. Mind you, head meters are used to record the pressure differential during the flow. Velocity meters, they are used to measure the pressure, and from the pressure one can calculate the velocity. So, let us see first of all the velocity meter, and in the velocity meter the pitot static tube is used. Pitot static tube is used to measure the pressure and hence to calculate velocity. Now, this pitot static tube, it measures the difference between the static pressure and impact pressure at a given point in the flow. This pitot static tube has an impact opening which faces directly to the flow, and as the flow impacts on the pitot tube, its velocity becomes 0 and the entire pressure is converted into the pressure, and that is measured through a manometer. So, let us consider a pipe where this is the flow, this is the center line, right. So, here we are installing a pitot tube this is a pitot tube So, this goes to the manometer, and this is the second point. So, here we attach a manometer this is a manometer and this records a pressure differential. So, as such, this is the low pressure side, and this is the high pressure side. So, let me complete now the pipe. So, this is the pitot tube. This is the impact point, and this particular hole it is used to measure static pressure. So, as the flow hits, so if I consider this is the plane 1 and the impact point is my plane 2. So, as the flow hits here, these are the flow lines, say air is flowing through this way as it hits. So, here the pressure, the high pressure, and you record the pressure differential along this through the help by the help of the manometer. So, its impact point of the pitot tube, it faces to the direction of the flow. So, as the flow impacts or as the flow strikes this impact point, its velocity becomes 0 and that is called the stagnation point, and the pressure which you record, that is called the stagnation pressure. So, we can apply now the mechanical energy balance between point 1 and point 2. So, applying mechanical energy balance, at 1 and 2. Now, since delta z is equal to 0, then we have say P2 upon rho plus 0, that is equal to P1 upon rho plus V1 square by 2, where V1 is the velocity of the fluid that we want to measure. So, at the point 2, since the air hits the impact point, its velocity equal to 0. So, that is why P2 upon rho plus 0 and P1 by rho plus V1 square by 2. So, as such, from here we can find out that P2 that will be equal to P1 plus rho V1 square by 2. So, from here V1 that is equal to P2 minus P1 upon rho, and in fact we multiply by Cp, and Cp is the pitot tube coefficient. To take into account losses due to friction, and its value for well designed pitot tube, it varies between 0.98 to 1. Now, here also you should record or you should note it that V1 that is equal to V maximum, because what we are measuring here, this is the center line of the flow. So, we are measuring the velocity at the center of the air which is striking the pitot tube. So, therefore, what we are measuring is the maximum velocity, because we have directed the pitot tube at a particular point. There could be a velocity distribution across the pipe. So, there could be there could be like this. So, if I consider this is a pipe, this is a center line. So, the velocity may be distributed, its distribution is like this. Say we have put our pitot tube somewhere here. So, pitot tube is measuring the velocity at the center, that is the maximum velocity. So, where this is an average velocity. So, from this the average velocity V bar upon V maximum that is equal to half for Reynolds number less than 2.1 into 10 to the power 3, and V bar upon V maximum that is equal to 0.62 plus 0.04 log of Reynolds number. So, that is, and this is valid for 2.1 into 10 to the power 3 less than Reynolds number and less than 10 to the power 4. So, that is how an average velocity in the pipe it can be calculated. Now, this particular expression is valid for low velocities of air. Now, for higher velocities, say for higher velocities of air, say greater than 60 meter per second, the compressibility also comes into picture. The flow becomes compressible in nature, and then one has to integrate the equation Tp upon rho, because rho is no more a constant. So, that will be equal to V1 square upon 2. For that we have to take assume a function, say P 1 by rho to the power kappa is constant. We consider ideal gas and adiabatic flow. Ideal gas and adiabatic flow, where kappa is the isentropic exponent. So, we have to evaluate this integral in order to find out the velocity through pitot tube pressure measurement, and we evaluate this integral, then V1 that will be equal to pitot tube coefficient square root of 2 kappa upon kappa minus 1 P1 upon rho 1 minus P1 upon P2 for 1 minus kappa upon kappa. So, that is how you will be calculating when the air velocities are very high, then the density cannot be taken as a constant, then it is called the compressible flow. So, in order to take into account the compressibility of the flow, one has to take density as a variation, and if we do that, then we get the velocity for higher air velocities through this expression, and the illustration we will see in the next class.